Let us learn about lattice energy. Lattice energy, represented by uppercase italicized U, is the energy required to completely separate 1 mole of solid ionic compound into its gaseous ions. And an example I can say is of lithium fluoride in solid state. To break it, you need to add energy that will be just enough to convert it to the gaseous state. So if you want to convert solid ionic lithium fluoride to gaseous ionic lithium fluoride, you need to add some energy, enough to do so, and we call that energy lattice energy. So let us use E to represent that energy required to convert solid ionic compound to its gaseous state, and it's going to be equal to a constant K, that's just a constant, times the charge on the cation. We know that cations are positively charged, so we'll call that Q plus, multiplied by the charge on the anion. We know that the anions are negatively charged. Okay, so Q plus is a charge of the cation, cationic charge, and Q minus is going to be the anionic charge, and then R is the distance separating the two ions. The lattice energy E is the force of attraction, the electrostatic force of attraction that attracts or puts the two ions together in an ionic compound. The cations and anions, they are held together by electrostatic forces, which must be overcome if you have to break an ionic compound in solid state and convert it to gaseous state. Bond breaking actually is endothermic, which is why we have to add this amount of energy to break it to gaseous state. So the lattice energy increases as the value of Q increases. You can see that here magnesium has a charge of 2 plus, fluorine has a charge of minus. So you probably just have 2 times 1 as the numerator of Q plus times Q minus, right? Which gives you 2. However, if you look here, magnesium has a charge of 2 plus, oxygen has a charge of 2 minus. So Q plus times Q minus is going to be equal to 2 times 2, which is 4. And that is the reason why magnesium oxide will have a stronger lattice energy that holds the cation and anion together than magnesium fluoride, because the charges involved are bigger in MgO than in MgF2. And you can see it's 2 plus for Mg minus for fluorine, 2 plus for Mg minus 2 for oxygen. The more absolute value of the sum of the charges or the product of the charges, the more or the higher the lattice energy. Here, lithium has a charge of +1. Fluorine has a charge of -1. So you see those are lower than the other two, MgF2 and MgO, so the lattice energy will be smaller. However, if you're comparing lithium fluoride and lithium chloride, the R factor comes in, because if the R value is small, knowing that fluorine is smaller than chlorine, the R is the distance between ions. So let us look at lithium fluoride, for example. Lithium could be this size, fluorine could be smaller like this. So if you look at the internuclear distance, it could be shorter, R here. So compare that to the one for lithium chloride, where that is your lithium, for example, and probably this is your chlorine, slightly bigger than fluorine. The internuclear distance will be longer. So in this equation, if the value of R goes up, then the value of lattice energy will go down, which is what you're seeing. Lithium chloride has a low lattice energy than lithium fluoride, because the distance here, R here for lithium chloride, is greater than the R internuclear distance of lithium fluoride. Okay, so the lattice energy will be lower because you're looking at R as a denominator in our formula. I'm going to explain the Born-Haber cycle for determining lattice energy. So these calculations that can be used to determine the lattice energy. And in general chemistry too, you're going to learn about Hess's law of summation of enthalpies. Okay, remember that when you're breaking bonds, you need to apply energy, which is why lattice energy is endothermic, usually a positive value, because you have to apply energy to convert the solid ionic compound to its gaseous state. So where does the process start? The process would start here, where you have the lithium and fluoride. Our goal is to make this lithium fluoride solid. Okay, so if you take the lithium by itself and fluorine by itself, lithium is in solid state right now, and the fluorine is a diatomic molecule. It has to be broken down to the elemental form. So we are going to sublime the solid. The lithium is a solid, so it's going to be sublimed to gas. And then the fluorine is a molecule, so it's going to be dissociated to gas, monatomic gas species. So the heat of sublimation is given as 155.2. Heat of dissociation is given as 75.3 kilojoules. Okay. And we can sum these up to give us the overall heat energy to transform solid lithium and diatomic fluorine to monatomic fluorine. Now, once they are in gaseous state, we have to ionize them, because remember, we are trying to make ionic compound. So we have to ionize them. They're split up. You see how this was chunky? Now the individual particles, this was diatomic. Now it's monoatomic. Okay. So now we'll have to ionize our gases. Remember, the lattice energy is defined as the energy that needs to be provided to convert an ionic compound in solid state to its gaseous state. Okay, so since we have the gas and gas, we need to change them to in the ionic form. Yes, keeping them in gaseous state, but make them ions. So we are doing ionization. For the metal, lithium, we say ionization because it loses an electron. And then for the fluorine, he gains an electron, so we call it electron affinity. The amount of energy release is 328 for fluorine, F to be turned to F minus the ion, and the amount of energy taken in to ionize the lithium is 520 kilojoules. So now we have our ions, which is why you see those charges. We have ions of lithium and you have ions of fluorine. All right, so when these ions now combine, you will need negative of lattice energy. Okay, remember, lattice energy is the energy required to break the solid ionic compound into its gaseous ions. So because we are going opposite, making the solid rather than breaking it, which is why we put a negative there. And the value is given as negative 1017 kilojoules. It gives us now the solid ionic compound. So I'll ask you, so what is the lattice energy that we require to change our solid lithium fluoride to its ions in gaseous state? It will be positive 1017 kilojoules, because just the opposite of the process. Okay. Now, the overall heat of reaction, enthalpy of reaction, is going to be negative 594.1 kilojoules. You'll learn the topic on thermochemistry later on, so I cannot go much into details, but I can tell you, to get this overall, you just sum up the energies from all processes. So you'll have to sum up delta H1 plus delta H2 plus delta H3 plus delta H4 plus delta H5. Those ones, when they are added up, you're going to get the heat of reaction, or the overall heat of reaction, and that process of summation of enthalpies is what we call Hess's law. Let us discuss lattice energies for some metal halides and oxides. Table 9.1 shows the lattice energies, and melting points of some alkali metal and alkali earth metal halides and oxides. So like we said, the formula for lattice energy involves a constant K. You multiply the value of the positive charge of the cation, the value of the negative charge of the cation, divide by the radius between the two atoms. In other words, the higher the positive and negative charge, the higher the lattice energy, which is the electrostatic force that holds the ions together in the crystal, and the lower the interionic internuclear radius between ion A and B, the lower the radius, the higher the lattice energy. The opposite is true. So in lithium and fluorine, we have lithium plus 1, fluorine minus 1. The lattice energy is 1070. Now, compare that to magnesium, where you have magnesium with 2 plus and a chloride minus. You see how you have Q plus and Q minus. There's probably just, you could say, sum up to 3. Absolute value 2 plus absolute value 1, it gives you 3. So the Q plus times Q minus is higher in magnesium chloride times compared to lithium fluoride. So you expect its lattice energy to be bigger, to be higher. Now let's compare the lithium fluoride and lithium bromide. The only difference is going to be the size of the anions. Okay. And so you expect that since Br is bigger, the R is going to be bigger than compared to the R, the radius between the Li plus and the fluorine. You're looking at, let's say this is lithium bromide. Let's say this is Li plus, and this is your bromine right here, the bromide. So the internuclear distance is going to be bigger compared to lithium fluoride, where the fluorine is smaller. So let's pretend that this is our fluoride. The internuclear distance is going to be smaller. And like we said, lattice energy equals to K times Q plus times Q minus over R. The smaller the R value, it's a denominator, the higher the lattice energy. Now, the other comparison we're going to do is between magnesium chloride and magnesium oxide. The difference here is going to be majorly the charge. So you have Mg 2 plus and Cl minus, or minus 1. If you sum these up, you're going to get 3. Okay, which will be a number probably we'll put up there. But for magnesium oxide, you have Mg plus and O2 minus. If you sum up these two, you're going to get 4. Now, if Q plus times Q minus is higher, you expect the lattice energy to be higher, which is why you see magnesium oxide has a higher lattice energy than magnesium chloride, because the overall Q plus times Q minus gives you a 4. It's higher. Now, if you are to do multiplication here, forget about the 3. Q plus times Q minus, this is going to give you a 2. This is going to give you a 2, just focusing on the 2 and the 1. 2 times 1 is 2. So between a product of 2 and a product of 4, the product of 4 is higher, which gives you the numerator Q plus times Q minus being bigger or larger value. Then the lattice energy is going to be bigger for magnesium oxide. Now, in the case of selenium nitride, Se has a charge of 3 plus, N has a charge of 3 minus. So now in that case, if you do Q plus times Q minus, it's going to be 3 times 3 It's 9, which is why you see selenium nitride has the highest lattice energy compared to the rest. And its melting point, so high, because you have a lot of electrostatic forces in its crystal lattice. Chemistry in action. The case of sodium chloride as an example. Sodium chloride, we mostly use it as table salt so that you add flavor to your food. The bulk of it is usually in chlor-alkali processes where you have sodium chloride and water being exposed to electric current, and the chlorine will break off to give you chlorine gas. Sodium and water will give you sodium hydroxide. Sodium can also be extracted by electrolysis. Hydrogen gas can be given out from the water. That's 50% of the forms of sodium that can be used, or the products of sodium chloride that can be used in day-to-day life. So like I said, you can use sodium chloride as a flavoring recipe in our food. It can be used for animal feed to force the animal to keep on eating and eating and eating for more milk, although you have to give more water when you give animals this sodium chloride salt. Can be used to melt ice on icy roads. That's what you hear whenever it's snowing. They say, "Oh, we need to pour salt on the streets," and then it can be used. Sodium chloride can be used for manufacture of other things, other chemicals, and also in making sodium carbonate somewhat. You are looking at a mine site, a site of mining of the salt, and we have a salt lake in Kenya called Lake Magadi. If you look it up, usually they pour water into some dams and let the water vaporize, and then they collect the salt.